In this presentation, I'm gonna talk about my work that we did at the University of Geneva in collaboration with all these people listed here. And it's gonna be about possible models for gravity change. And we focused on the lava fountaining activity at Mount Etna. And before to start, I have to say that this presentation is listed like my contribution, and then Valentin would take over in the end, but they do apologize because at the moment all the Geneva group is taking measurements for lava fountaining in La Palma. And I'm not sure whether they can join up looking at this picture.
I don't join, Luigi.
You are here. Okay.
I'm in the car, so.
Okay. But they send us this nice video that I can use as a start for what I'm gonna talk later on. So I try to be fast though, because I have to cover all the time. And so basically, if I jump to the presentation, the University of Geneva is the leader of the task 4.4, which implies the use of the gravity data for hazard analysis and early warning. So basically the idea is that we can make use and try to understand which information we can take from the gravity data that are part of the Newton G project, and how to use them in terms of understanding patterns and anomalies in the gravity which are related to the eruptive processes at Mount Etna. And we work in collaboration with the monitoring group of Osservatorio Etneo INGB and with the GFZ team that showed the theoretical modeling that was nicely presented before by Mehdi. So this is a picture that I borrowed from Robert Tilling publication in 2009, and it shows a volcanic arrest. So on the y-axis, you have the intensity of whatever monitoring parameters. In this case, for us, would be the gravity. And you see that the graph has a clear marked escalation. And this is the unrest. And that can evolve in a complicated matter, but the early warning or the hazard assessment is just confined in a very short time window where we have to communicate to the officials what is the evolution of this unrest. If we go to a major eruption or a return to the dormancy, it can be complicated, but that's is not part of this talk, because basically we are going to only focus on the unrest and try to understand whether anomalies in the time series can be used for informing the officials, or at least to understand what are these anomalies. And as I said, the character and the duration of the arrest can be highly irregular. There is no clear patterns, but we are on the range of people that do think and believe that, at least in volcanology, physical modeling can help to understand the processes and understand at least some of the patterns related to some of the observable. And in this case, as was also mentioned by Daniele this morning, gravity can inform us on the mass migration underneath the volcanoes. Our approach, in order to try to understand and to dig into the data, is to start from a physical model. And Mehdi nicely introduced the compound dislocation model that I'm going to use later on in the models that I'm going to show you. And this model, we apply a kind of stochastic scenario. So we simulate Monte Carlo the input variables of the model, and we get an output of distribution. So a variety of possible realization of this model that we are going to compare with the observation. And for the observation, since the wide eruptive styles that you can have at Mount Etna, that ranges from strombolian lava fountaining activity to lava fountaining which are leading to paroxysm, huge explosive eruptions. We have dike intrusion that can feed lava flows from the fissuring of these dikes. And also the gravity can tell us about the changes within the volcano pumping system. We focused on the lava fountain activity because this is part, as I showed you in the video before, of the expertise at the UNIGE, but it's also one of the most frequent eruptive styles at Mount Etna. I guess this year we are still at the 56 paroxysm going on. So that's a good way to go, also because the lava fountaining would produce a hazard related to the tephra dispersal. And also the other good point is that for the lava fountain in 2011, as Daniele showed, there are gravity data available. So waiting from the data which are coming out from the Newton G project, we could use basically the data from these episodes in 2012. So in the summer of 2012, they went to this ECPN location, which is southeast of the crater, just 1 kilometer apart from the now north-southeast crater, which was the focus of the lava fountaining. And they could record 9 lava fountain episodes, and we have 7 of them with usable gravity data. So remember this geometry, because from the crater to the station, sorry if it's very small here, but this is the geometry that I'm going to use in our simulation later on. So the data, as presented here for 4 episodes in this busy plot, they have on the top panel the ground shaking, and the ground shaking is important, as I show you later on. And in the middle panel, there is the gravity change, and then you have the optical imagery to constrain the start of the lava fountaining, or the transition between the strombolian activity and the lava fountaining. You can see it better here. This is the one plot magnified. And you see that as the ground shaking, as the amplitude of the ground shaking is going up, at some point, the light gray lines, which are in the middle panel, they show a very high frequency content, which means that at some point when the ground shaking is so high, the gravity data are not usable anymore. So even when you low pass filters the data, as the black line would tell you, you see that at some point there is a break where we cannot use anymore the gravity change. And this coincides basically with the start of the explosion at Mount Etna. So the characteristics of our data are for 7 episodes. They have a duration of this transient, which is between 2 and 4 hours. There is a gravity change of 40 to 80 microgauss, and the mass eruption rate, as Valentin will show you later, they range between these 2 quantities. And one explanation for that, which is our working hypothesis given by Daniele and co-authors in this paper, is that the gravity signals is related to the transition phase of the magma and the increase of the volatile phase in the magma, so basically gas, that will shift the eruptive style from a strombolian activity fed by a gas slug uplift in the conduit to fountain activity, which is dominated by the gas annular flow. And the gravity would be related to the decrease in density from a liquid phase to magma phase. So this is our working hypothesis that we are going to test, at least with the second model I'm going to show you. And this is a plot summarizing the time series that we have. On the x-axis, you have 0, which is 12 hours, almost 12 hours before the loss of the signal that we have for the data, and each color represents one of the 7 episodes of lava fountaining. And on the y-axis, you have the relative gravity change. What was done in Newton G, and it's everything written and reported in the deliverable 4.2, if I remember correctly, that they stack up all the data, they do average, and they low pass filtered the data to end up with this black line here, which is the representative gravity change induced by those lava fountaining episodes. And I reported here, this is the low pass filtered gravity signals. And basically for now, we are focusing only on the last 3 hours of these episodes, which we do believe compared with the optical and thermal imageries that are related to the transition between the Strombolian and the lava fountain activity. So basically, in other words, we are going to focus ourselves on this anomaly, on this decreasing gravity, which is transient and lasts for 3 hours. So now I walk through our modeling approach, that it's still working process, and any of your comments and suggestions, even critics, they will be welcome because they will help us to improve the model. In this case, we started with a classical approach, so coupling an elliptical chamber with a cylindrical conduit, as you can see from the plot here. And we use a combination of the compound dislocation model presented by Mehdi with a line mass model for account of the gravity change of this cylindrical conduit. The geometry is variable, and this elliptical chamber is pressurized at the beginning, and there is a threshold for excess pressure that's gonna break through the valve and fill up the conduit, which is an open rigid cylindrical conduit, and the magma will rise according to the overpressure of the magma chamber. In this case, and for this case, we do not account for volatile exsolution or bubble growth in the conduit. And here I show you one possible simulation where the magma chamber is still overpressurized, and then we break the seal, the overpressure exceeds a threshold, and then it starts to fill up the conduit. And the gravity is measured at the gravimeter here, which has the same geometry of the 2011 configuration for the spring gravimeter. And on the top right panel, I'm going to show you the individual contribution of the decreasing gravity due to the mass loss in the chamber, and the increasing gravity due to the filling up of the conduit. And on the bottom channel, you see the total, so the sum of the two. As you can see, as the magma is leaving the chamber, gives a decrease of the gravity, as I said, and the conduit is instead giving the opposite signals. And the total gravity chamber can reproduce a general decrease of gravity, which is similar to the data, but has some differences. And we were not happy with this model also because we have to use a kind of very low magma compressibility, which is maybe unrealistic. What I want to show this model may not work for our case, but in general, it's a flexible model that can be changed in terms of geometry, magma compressibility, and position of the gravimeter, for example. It will give you the gravity contribution of the chamber and the conduit and the total gravity with a different shape, of course, up to a total increase of the gravity in this particular configuration I'm using here, where the magma chamber is very deep, so the amplitude of the signal is very low, and you have an increase of the gravity change that would be measured at this hypothetical gravimeter here. So in order to improve our modeling, we were not happy with that. We just jumped to another approach, where we are simulating an ascending dike. So basically, we are simulating an ascending tensile dislocation, which is a 3D dike. And we constrain the volume of the dike and the velocity from the mass eruption rate and the duration that in this case, I keep to be 3 hours for the transient that we are seeing. And the initial geometry of this model is that we are placing a dike, which a strike would be northeast southwest, which is coming from the opening of the fissures or the crater at the north-southeast crater. For this one, we account a density decreasing with height, with the uplift of the magma due to gas, to the gas expansion due to the compression. And here it's a possible density profile and a gas volume fraction. And you can see here that you have the dike where geometry is changing, and as you can see that also the opening, which is color coded, it's increasing as the dike approaches the surface due to the gas expansion. And what we did, as I mentioned at the beginning, we simulate this model via Monte Carlo, so a stochastic approach. And for now, we are only simulating the geometry. So basically the depth, which is now in this range between 3 kilometers plus minus 1, and the strike, which is 50 degrees off the northwest-southeast direction. And in this case, we can produce 10,000 Monte Carlo simulation, simulating independently depth and strike from uniform distribution. And all the colored curves here are the possible realization of the model. And I'm superimposing in the gravity panel the signal or the reference signal that we have, which is the black line. We have the model gives us a density profile with depth, which are on the top right panel. And then we have also the uplift of the gravimeter, which is in the configuration of the 2011 lava fountaining. And as you can see here directly, you have our model, it's giving us a lot of deformation. That maybe it's a problem because it's not seeing deformation during the lava fountaining episodes. What I did, I just take as a best fit solution of the simulation. And in this case, sorry if I change the color, but now the model is the black line. So this is the model simulation, which is the most closely or has the lower misfit compared to the gravity data, as would be this equation. And in this case, you see that the model is perfectly able to reproduce the gravity change. There is a very nice match. The density profile would be this one, but again, we can predict with this model a 40 centimeter or a bit less than 40 centimeter uplift at the ECPN station that, although it's a transient, so it lasts only for 2 hours, it seems to not appear in the GPS data. And what I wanted to comment on is also that the total gravity basically is dominated by the uplift. So if you take the total gravity and you subtract the free air contribution, then you see that the most of the decrease of the gravity is due to the uplift of the station. So, but this is a model that we can use, and I'm going to conclude and give the ball to Valentin, just saying that anyway, we developed two time-dependent model. They can produce a gravity change scenario, and they are fast and quick to run. It lasts only a few seconds, all the Monte Carlo simulation, for example. They are tailored for Mount Etna and for the 2011 lava fountaining episodes, but in principle, they can be applied to any type of volcano. The only caveat, which is listed in the end in this conclusion, is that to have a good coverage of gravity or good gravity data, and also independent information on the deformation, which is going on during the eruptic activity. For Mount Etna, basically, we have problem with the chamber and conduit model to reproduce the amplitude of the transient, which is a bit lower, or at least it requires even lower magma compressibility to be reproduced. While the dike ascending model, it's very nice at fitting the gravity data, but it's predicting a large deformation. And this is may be related to the fact that we are anyway assuming an elastic half space, where close to the surface, maybe this is not really the case. And for this one, I finish my presentation. And I don't know if you, Valentin, want to take over. Otherwise, I can.
Yeah, sure. So I will share my screen. Is that okay, Luigi?
Go ahead, please.
Okay. So can you see the screen? I don't know if.
Yes.
Okay. So as Luigi said, I would like to apologize because we are at La Palma with Costanza Bonadonna. And so unfortunately, I don't know if she will be able to make it because the activity is quite, I mean, the volcano is quite active. So it's kind of the rush in the field. And also, I would like to apologize for the connection because it might be a bit unstable. So in any case, wait, I will just put my video. Okay. So in any case, if you have any troubles understanding what I am saying, don't hesitate to interrupt me because I'm going to be fast anyway. So it's just for presenting myself to you all guys, and just to say first that I'm pretty happy to take part of this nice project, because I think also that gravimetric signals can be an important tool for monitoring the activity, in particular at Mount Etna, but not also, I guess. So for those who don't know me, so I'm Valentin Freret, and I was a postdoc researcher at the University of Geneva, so hired in the framework of the UNIGE project. And so I'm taking the lead of Luigi's postdoc now in order to continue the project with the same philosophy, but we taking another axis that I will explain now. And at the end, perhaps to try to mix this new philosophy with the model of Luigi and try to constrain everything. So basically, the aim of my work, and I mean, the objective now is to try to compare the remote sensing data so I acquired before at Etna. So in particular, during this sequence that Luigi just shown you, and with remote sensing data acquired mostly at Mount Etna. So as I told you, I was working the framework of the UNIGE project, and the aim was to find the best strategy to derive what we call the eruptive source parameters. So which are, for example, the mass eruption rate, the total mass of the eruption, the plume height, and in particular as well, the total grain size distribution of the particles. And all those eruptive source parameters are key parameters to initialize what we called the volcanic ash transportation and dispersers models, which are used operationally by VAC, for example, to try to forecast and model the dispersal of tephra plumes during an eruption. So those parameters are pretty important to constrain in real time. So to do that, we wanted to find, as I said, the best strategy, but using a large set of remote sensing systems. And this is totally possible at Mount Etna because there is a lot of various remote sensing systems, as you can see on this graph. So basically, you have several Doppler radars, which are working at different wavelengths. So basically, you have Vordoad, which is one of the radar operated by the Laboratoire Magma and Volcan and the Observatoire de Physique du Globe de Clermont-Ferrand. And it's basically, so without going into detail, it's measuring the mass and the velocity of the projections just next to the vent at Mount Etna. So mainly, it's not only focusing on the new southeast crater, but also at the other active vents. In addition, we can have access to satellite radiometers, so which are giving information on plume height, mass eruption rate, and also ash concentrations of all particles that are below 20 microns. And then we can have access to infrasonic array, which give pressure and also a proxy of the mass eruption rates, and so on. So the aim is to constrain and compare all the outcomes from all those sensors to build multi-sensor strategies, and also to have better constraint of each parameter for near real-time applications. And so now what I want to say just to, okay, we have a lot of data, so at Etna, and you now are trying to understand what you are seeing with the gravimetric signal. So the aim here is can we find a link between the pre-eruptive gravity signal and the syn-eruptive measurements that we've made with the remote sensing systems? So in a sense that using the gravimetric signal, perhaps we could be able to predict or to try to forecast the strength of an eruption. So this is the axis we would like to work on. So Luigi already presented this data set. So this is the one I've used so far. Okay, sorry. So this is the one I've used so far. So this is the sequence of 9 paroxysms acquired by a gravimetric station. So this is the paper of Daniele Carbone et al. 2015. So this sequence is composed of 9 paroxysms, for which of them 7 time series were sufficiently good to provide good gravity signals. So this sequence is composed of moderate paroxysms with plume heights that are comprised between 5 and 13 kilometers above sea level. And the total mass of this paroxysm are spanning one order of magnitude, so between 1 times 10 to the power of 8 to 2 × 10⁹ kilograms. So for this particular sequence, we have several available data sets, so which are composed of lava volumes, plume heights, or mass eruption rates from visible or satellite imagery. We have pyroclastic volumes that are retrieved by infrared camera. And also we can have access to total mass and mass eruption rates retrieved by Doppler radar. So with an example of the Voldorad 2B Doppler radar. So the motivation of this work here is to try to compare then, as I said, the remote sensing data with this sequence of gravimetric signal. So as Luigi told you, so typically for this typical paroxysms, so we have decreasing changes prior to each recorded paroxysms. So you have here a time series in black of the gravity changes as a function of time. And in blue, you have the mass proxy. So the mass recorded by the Doppler radar Voldorad 2B. So you can clearly see the decrease in the gravity signal prior to this, the start of the eruption, which is at that point here. So what we've done so far is to try perhaps with a stupid way, but try to compare very simply the mass retrieved by the radar for each paroxysms and the maximal amplitude of these gravity changes. And as you can see on those two graphs, even though it's rough, we can clearly see that there is a rough negative correlation between the maximal amplitude of the gravity changes and the total mass retrieved by the radar on the left. And also you have a rough positive correlation between this maximal amplitude and the paroxysm duration retrieved by the radar. So one of the things is that we can draw an hypothesis now is that the gravity changes are somehow related to the quantity of erupted pyroclasts measured by the Doppler radar. So this is the starting point of this. And what we want to do for the next few months is try to investigate whether this correlation is valid for other remote sensing systems, so such as another Doppler radar, which is an X-band Doppler radar operating at the airport of Catania, but also compare these gravity signals with data obtained on tephra fallout deposits. And we will try to know also if these correlations are also valid for the new sequence of paroxysms, using, for example, infrared-based satellite observation, the X-band Doppler radar, and as I said, tephra fallout deposit analysis. Also, we would like to know if those correlations can be, are these correlations general, or do we have one correlation per sensor? So we understand if we have one correlation, so then to see whether the gravity signal help one sensor or another one. So we need to ask that question as well. And the final question is, what if no correlation is found? So this is why then we can come up with model to try to understand whether this gravity signal have can give information on the pre-eruptive activity or also in the eruptive activity. So these are the huge opening questions. And the fact is, like Costanza and me are not expert at all in gravity signals. So we are just here to try to bring our knowledge with the remote sensing data and the tephra fallout deposit analysis to see whether we can combine the two data sets and to try to find a very good strategy to forecast Etna paroxysms. So this is the aim so far.